It's recording. Okay. Welcome everyone to ACM-AI's first workshop. I'll be covering. My name's Stone. I'm the current president of ACM-AI, and I'll be covering about pathing algorithms that are typically used within AI. So if you look at the picture on the right here, you can actually see like just a couple maps, just standard maps. This is like a random map I found online from this website called Red Block Games. The main goal of like pathing is really what pathing says. It's just going from A to B. So like, we're going from this star to this X, right? Same thing. If you guys haven't heard, we're running an AI competition right now. It's called Hide and Seek. This picture on the bottom right was actually taken from one random game I found there. And one of the main goals as a seeker is, right, if you're hiding and seeking, as a seeker, you got to find your hiders, right? So how do you find your hiders? There's a bunch of walls in the way. Like all these yellow tiles are walls, all these zeros are like empty tiles. One of your main things you have to do is path around those walls and find the hiders, right? So I'll be talking a lot about that today. So basic pathing, what is it? Going from X to Y on a graph or a map. So the main things we want to achieve is efficient, fast, and accurate pathing. So what I mean by that is efficient means like each step of the way when we're trying to decide on the next place to go. It's not computationally expensive. For example, choosing a random direction to go towards to like move in a map is very efficient. But obviously that's probably inaccurate if you want to find the best optimal path to go somewhere. And if we want it to be fast, we want to be able to find our most optimal path as fast as possible. So there's always this balance. Do we take a less optimal path but find it faster? Or do we take a more optimal path but spend more time? It's always a balance. So there's many applications for this. One application is in robotics. Robots aren't humans, so we don't really care about their lives. So they're able to navigate through dangerous radioactive areas to people. And in fact, I think during one of those nuclear disasters, I think Fukushima, they had some robots programmed to like navigate through the waste. So through that, they were able to like explore the aftermath of the disaster. And in many games, AI is needed. So some kind of AI is needed for your games, right? Like think about all those zombie pigments, or all those like, I don't know, zombies, spiders, skeletons in Minecraft. They all use a pathing algorithm to find you, right? They can see you through a window, so they walk around the wall and like go through your door or something, and then like attack you. So for them to be able to do that, they need to find how to go from seeing you in a window to walking around and going through your door. And then a bit more abstract kind of idea of what pathing really is like pathing in machine learning, which is like a lot of algorithms and models in machine learning. The main idea is we have an evaluator function that returns some loss, and our goal is to get a model that has the least loss. Don't worry about what loss is. In fact, Edward Yang, he's another member of ACM-AI. He'll be talking a bit more about like validation loss or like accuracy in his MNIST workshop later, so don't worry about that. Just think about pathing as trying to go towards a certain direction. And the motivation is oftentimes we can't find the best path all the time. We're often given local map information and can only perform local movements. For example, we can't teleport, right? We can only do a local movement. We can't like jump from A to B by teleporting. Think of like the zombies in Minecraft. I think Matei is saying they can only walk in a straight path. That is a constraint, and we have to work with those strict constraints. So if we can't jump 10 tiles forward, we have to take step by step. And which step we take is really crucial, and how to do that efficiently is also really crucial. So the question is, how do we get from one place to another as fast and accurately as possible, given the constraints of local map information and local movements? And so today I'll be covering various pathing algorithms from very basic like greedy algorithm to a much more advanced A-star algorithm. Right. Why is this not changing? Someone just put A-star question mark. A-star is an algorithm that's kind of complicated. I'll explain a bit more about it later. So first thing I'm just going to briefly talk about is just graphs, the notion of a graph. When you're thinking of like a game, when you have like a 2D map, right? A 2D map is composed of X and Y coordinates, tiles, right? Think of the Cartesian plane. Well, if you think of a graph is composed of nodes and vertices. So like if you look at here, I don't know if you can see my cursor. All these white circles are nodes, and all the lines are edges. So what we kind of do is we represent a lot of what we see as nodes and edges. And then if you apply this to real world, right, we can think of like these Google Maps as graphs. And in fact, this is how Google Maps encodes some of their like route finding. So if you look at all these roads and intersections, right, we see that Google actually splits these roads and intersections into nodes. And then what it does when it tries to find the best path for you to go from, let's say, your home to like UCSD or your home to like, I don't know, Rogers Market, it will kind of traverse this graph, right? It'll go from node to node to node, and it can only go from one node to another by traversing an edge. So the same thing with maps, right? If we're trying to find like which street path you can take, each street is kind of represented or segmented into different vertices and nodes, and each intersection is like a node. So we know that we can change direction at each intersection, or keep going straight along a street, which is also just an edge. So now if we expand this to like our more specific example we're looking at, which is like 2D maps, which I'll be using all our examples based on 2D maps, just to keep things simple. A 2D map is essentially composed of square nodes, right? You have a bunch of Cartesian plane points. You have a lot of squares, right? So let me see if we get a picture. Like you can see that we have all these like yellow squares, and this is like a grid. For this entire grid, every node, every tile on the grid is a node, and it is connected by an edge to all of the adjacent tiles. With that in mind, I'm going to talk about the first algorithm, which is greedy pathing. And the idea is that we base this on like a greedy kind of algorithm. What we do is we are always looking to choose the next best step to move from tile X, node X, to node Y, right? So the code on the right kind of just shows some pseudocode. It's a little bit like JavaScript, but it's really just pseudocode. And yeah, it basically demonstrates how, given a current position cur and a target position we want to go to, or a target node, we want to take the move that moves us from the current cell or current tile closest to our target. And the reason why it is greedy, because we're trying to take the closest best, or we're trying to take the best move locally. So like, we're not thinking ahead, we're just thinking one step ahead, which is what's our next best move. We're not considering the fact that our next best move might lead us into like a hole somewhere, or like some corner that we can't get out of. That's why it's greedy. And then if you look at a function on the right, we're essentially just doing this. First, we want to find the best cell to move to, the best tile, and we take a value called closest distance. And what we want to do is we want to find a cell that we can move to that has the least closest distance. So what we kind of do is we run like a for loop, right? We run a for loop over each of the neighbors of the current cell we are on. And for each of those neighbors, we measure the distance from that neighbor cell to the target. And if the distance we measure is closer than the closest distance we've measured so far, we store that cell as the best cell we have seen so far that's closest to our target. And we keep doing that, and we return the best cell. Very simple algorithm. It's very fast, very quick, very low storage. Yeah, and the speed is like O of n, where n is the number of neighbors of a current node. Someone just asked a question like, wouldn't that go just in a straightest line? In fact, it won't. Well, okay, so there's some other constraints. The reason why we have this is also because like maps aren't always just simple empty maps. If it was just an empty map, obviously you just go in a straight line. But there's always obstacles, right? If you're in like a really broken down place like the Fukushima disaster, that nuclear plant, there's a lot of rubble around. So the robots have to navigate around the rubble. And I'll show in a minute an example of that using like a map generated from our competition. I just also want to point out there's different distance heuristics. So if you look at the code on the right, there's a function called distance that takes in like a cell, like the neighbor, right, and the target cell. And the way distance works is basically you can return different kinds of heuristics. One heuristic is called a Euclidean distance, which is kind of like the standard distance you learn. It's like the actual distance on a 2D plane. So the way you'll calculate it is like take the square root of the dx, change in x position plus squared, plus the change in y position squared, and you take a square root. And then another distance heuristic is called taxicab or Manhattan distance. I don't have a good picture of it, but think of it as just measuring the distance. When you do that, is just taking the change in x plus the change in y. So we don't take the hypotenuse as the distance measure. Instead, we're just adding the x, or the y and the x, and that's our Manhattan distance. The reason why I was actually named after Manhattan distance because Manhattan is famously known for having like a grid like road structure. Like the entire New York is like squares. It's just squares. So you can't like cross between buildings to go somewhere. So really, your true distance, if you're in a taxi cab trying to go from one place to another, is the number of like ups and downs you move, right? Ups and rights, right? Whatever. I'm gonna take you guys through quickly how we can greedily path. So Ashan asked a good question. How do you take consideration of a wall in your distance calculations? So for this distance heuristic, we don't actually take consideration of the wall. We just measure the absolute distance from our current cell to our target cell. So I'll show you how we go from like F4 to X. So for example, let's say we're starting from the number 4 here, and we want to go to the blue X. We see that immediately that in our algorithm, we're looking through each of the adjacent tiles, right? We're taking the neighbors of 4, our current position, and checking them. We want to find the closest one to a blue X. Well, clearly the closest one is actually the one that's down south, right? That south one. But however, it's actually a wall. So all these yellow tiles are walls. All the 0 tiles are tiles we can move on. But since we can't move on to the yellow tile, we need to greedily choose the next best option. And then if we look around, right? The left and right positions don't work because they're not as close as this position here, where the green line goes. So the green line is the path we're actually taking. The yellow circles represent paths or like positions we could go to, but they're not as good as the greedy best path, which is the green line there. And if you measure it, right, that green line is going to a place that's closer to the blue X than any of the other places. And you could argue that going southeast or bottom right is actually the same distance, which it is, but we can just arbitrarily choose one or the other. And now the next thing. So the next part of this is now we run the algorithm again, right? We check our surroundings, and then we see that of all the surrounding positions, this is the most optimal because this takes us the closest to the blue X, our target cell, from our starting cell. And I marked the other places as suboptimal because they're farther away from our target. So being the greedy cell VR, we take the closest position, which is going in bottom right. And then from there on, as Thomas mentioned earlier, right, we kind of just go straight because that is the most optimal. We're going directly towards our target. So we actually just go straight. And I marked a couple other tiles as suboptimal because when we're running our algorithm, we might be checking them and realizing that those are farther away, and we might as well just go south. And then we enter the same situation as before. We're just going to hit a wall. We realize we can't go into the wall, so we choose the next best option, which is going bottom right. And then again, we apply the algorithm again, and we go bottom left. And then we reach our target. So this is an example of how greedy pathing kind of takes you from X to Y. And it works relatively well. Someone just asked what's a tiebreaker. Can you elaborate? Feel free to talk into the mic. I'm not sure what you mean by tiebreaker. Sure, math at random is a possible tiebreaker. Yeah, so when you have two paths have the same distance, it's really up to you. In the algorithm I showed earlier, you kind of just choose the first one you look at. Or, sorry, not choose the first one. You just choose the first one that is the closest distance, and the other ones won't be less. For tiebreakers, it really doesn't matter because the greedy algorithm doesn't have a specification for tiebreaker, because if they're both greedily the same value, it doesn't really matter. Any other questions about greedy algorithms? If not, I'll go to the next slide and begin talking about the caveats. Why greedy pathing is actually not good. And Bryce mentioned that there might be a better way to do it where the neighbors function doesn't include the walls and what it returns. Typically, something like a function like that should return all the possibilities and you just filter out the walls. So now this is a problem with greedy pathing. So if you look at this, where's my... So if we look at this, there's many downsides to pathing. For one, it's not accurate at all. And when it's not accurate, it's because it literally doesn't path to the target you want to go to sometimes. So for example, if you look at the number 4, that number 4, if you start from there, you cannot apply the greedy pathing algorithm and get to 6 and 8 because of the yellow walls. And the reason why is, like, look at this. If we apply our greedy algorithm, right, we'll obviously go straight towards the 6, right? We keep going straight left, and then we realize there's walls everywhere, so we have to go straight down now. But now we're in an issue, and now we're in something called a U-shaped trap. This is when we enter a position where our best possibility, like our only position we can move in, is a worse position than our current one. So if we look at the green circle, that circle is the closest you can ever get to 6 and 8 without having to go all around that giant wall. Does that make sense? And you kind of see like it's a U, right? Do you see like the U-shaped wall in here surrounding the green circle? So with that issue in mind, greedy pathing fails here. Greedy pathing is fast and efficient, but it really doesn't get you to the right place. And so at this point, there's actually a lot of different like ways you can like fix this, and I'll be explaining one of them. Oh, fun fact, with these U-shaped traps, the original person who coined the term, the way he resolved these traps wasn't using a better pathing algorithm. Instead, in his game, he just got rid of all U-shaped walls. So without U-shaped walls, you can always use greedy pathing. Yeah, that's an interesting note. Anyway, next slide. Oh, I already showed this. Yeah, I already showed this one. You see that you just can't get past the walls. So the next algorithm, I'm gonna go. Oh, I don't know what game this was. This was on Wikipedia. Some game designer or something just found that problem that his like AI units were getting stuck into U-shaped walls. So as a result, he either had to make a better algorithm or get rid of U-shaped walls. He chose to get rid of U-shaped walls. Bug pathing is another popular algorithm. It is basically as fast and it's a little bit slower than greedy, but it's pretty fast and efficient. But then again, it comes with the downsides of not being always accurate and doesn't always have the most optimal path. And I'll show that caveats later. Bug pathing is kind of like sticking to the one side of a wall trick. If you guys ever done mazes, one of the tricks for solving a maze is keep putting your hand on the right wall and keep holding your hand on that wall until you get to the very end. And then some of you guys might already realize that this trick actually doesn't always work, and there's some caveats where you might end up just going in a circle, and I'll show that later. So I'll show you one variant. There are many variants for bug pathing. I'll show one, and this is sometimes called bug 2 by some people. The idea is you start from position. Let's say you want to go from 4 to that position that's marked by the blue line, right? That's in like the top left. What we first do is you create a line, and we call this. This is the technical term is called an M line. So we create a line from our source, our starting cell, to the target cell. And then we greedily go towards our target. And then our next step is if you hit an obstacle such as the wall, we follow the wall that putting our right hand on a right wall or a left hand on a left wall and keep following the wall until we hit the M line we created earlier, which is the blue line on the picture to the right. And then we perform greedy pathing again, and then if we hit, and we just basically go back to step B. And then we keep doing that until we reach our target. So this is efficient, easy to compute, but there's some problems with it, which I'll show later. So I'll show you how this works. There is an example. So let's say we want to get from this 4 to the end of the blue line. All right? If we do greedy pathing, right? Greedy pathing will take us as far as here. And then we enter our U-shaped trap again, right? Because any other position we can go to, the only open positions we can go to is up or bottom right. But however, both of those positions are farther away from our target. So what we do is now we take step B now, or step C, and we start following the wall. And let's just say we want to follow the wall to our right. So we follow the wall. This is the purple line. And we keep following the wall until we reach the red line, blue line again. So does this following the wall make sense? We kind of just keep sticking to the same side. So like a way to code this is like you add in a direction to your pathing, and every time you move in a direction, you update that direction, and that way when you have a direction you're going towards, you can have like a reference of what's right to you and what's to the left to you. And so by making sure there's a wall to the right of you all the time, you follow that wall, and then once you reach that blue line again, as we have here, the M line, we switch back to the greedy path algorithm, and then we greedily path all the way to the target, and we've reached the target. So remember, this is like the same map we've shown before. Previously, if we just applied greedy algorithm, we would have been stopped. We would have been stopped in the middle, by those tiles that are marked by the red circles. And if we were stopped there, we wouldn't be able to get to our target. But with bug pathing, we were able to reach there. But now just some issues. So I'm going to show you a problem with bug pathing. Suppose we did our greedy pathing and got to a place, and now we want to start following the wall again. Now suppose we randomly decide to choose to follow the left wall instead of the one on our right. Well, here's an issue. You see, we curve around the left wall, right? You kind of know this is a small issue already because we're moving away from our target, which is a little bit weird. But it doesn't matter. That's just how bug pathing works. And because we only have local map division and we can't like analyze the whole map easily, this is probably our best option. But as we keep following the left wall, you'll notice an issue. Like we're following this left wall, and then all of a sudden we're back on the same path again. That's a bit weird, right? And then if you notice, if we keep following the left wall, right, we never reach the blue line again. And if we never reach the blue line, we'll never switch back to the greedy pathing algorithm. So this is one of the main issues with bug 2, or like the bug pathing algorithm in general, is that you can easily get stuck in loops. And you'll never find your way to the end. There are some ways to counteract this. One way is to store a bit of memory to keep track of where you've been. And if you've been there already, switch the wall you're following. However, even if you're just switching the wall you're following, that doesn't always work, because like it could be that you can have 2 sets of island walls that make you go run in circles all the time. So now instead of running through one circle on the wall on the left, you're running in circles around the wall on the left and then switching to the wall on the right and running in circles again, which doesn't work. So yeah, that is bug pathing. Do you guys have any questions about bug pathing? Does it make sense? Alright, if Thomas is okay, I think you guys are all good. Let's see. Next. Okay, someone said oof. What does that mean? Oh, okay. I don't know what that means. Next example. So next example I'm going to go through is BFS. So it's basically, BFS is a typical graph search you probably learn in CSE 12, CSE 100, or whatever. Yeah, Ishan knows. Thank you for the definition of oof. I'm now enlightened. But anyway, BFS is typically a graph search, so you use it to search your entire graph for a node. So we apply this idea back to our map, right? Our map is essentially a graph, and if we want to go from one node to another, we can just apply BFS. So we apply BFS starting from some starting node, and you want to go towards a target node, which is somewhere in the graph, or otherwise known as our map, our 2D map. And the most important part about BFS that separates it from what's another a graph search algorithm known as DFS, depth first search, is that it uses a queue to make it breadth first. So the idea of using a queue is that the way we search a graph is by gradually searching. And I'll show you an example of what it looks like. So give me a second as I switch tabs. I'm going to have to change screen. Yeah, Bryce, it should definitely be in CSE 100. All right. Can you guys see the screen? Alright, I'll show you an example of how BFS works. So the idea of a BFS is we have something called a frontier, which is our queue. And what we do is, starting from a current node, for each node in our frontier, we iterate through our frontier, we expand our frontier. And so I'll show you just like a quick animation. The first step is we add all the neighboring nodes. So we take like the left, up, right, and down nodes, add it to our frontier, and every node in our frontier, we're going to go through it and search it and check if it's the position we want to go to. So suppose we want to go from this position here to all the way here, right? We want to go somewhere here. So for each node in our frontier, we add all the new nodes. So we see that we searched the right node, we marked it as gray because we searched it already, And we added the new nodes that we haven't searched. Most importantly is we also make sure we don't add nodes we've been to already. So we see that this slowly expands out. We never add old nodes, we only add places that we've been to already. Sorry, we haven't been to already. So keep expanding, and slowly you'll realize that we will have searched every single tile on the map. Now, for a BFS to become a pathing algorithm, we need to store something called a came from set. Here, came from. So this came from map maps a node or a map tile to the tile it came from. So remember how like each node in our frontier, right? In this blue frontier, for each node in this frontier, we're checking each of its neighbors, these green tiles. And for each green tile, right, we're going to put these new tiles that we haven't seen already or are not in our frontier already into our frontier and make them blue, which is because they're in our frontier now. And so the way we check if a node has been in there, right, is by using a map, such as like those Java hash maps. So a map also acts like a set where every element or every key in there is unique. So what we can do is we take each of these map tiles and put them in the map and map them to a previous tile, and it should be unique. We know that if came from doesn't have a node already from his neighbor, that means we've never looked at that and we just put it into our frontier. So that's why we put if next and graph.neighbors of a current node is not in the came from map, we put that next tile, which is in the neighbor of the current node, into our frontier queue, and then we update the came from map to tell ourselves or make a record of ourselves that to get to this next node, our neighboring node, we have to come from the current node. And what you can see is that it creates breadcrumbs. Do you see all these arrows? So that came from map creates these arrows. So suppose you want to go here. You want to go to this X. Well, based on our came from map, we know that this node came from this node. This tile, this map, this node came from this tile, which came from this tile, which came from this tile, which came from here, 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 here. And we just kind of follow the purple line, which represents our came from set, our map. And we keep following all the way back to our start point. And then that creates our path, right? We just follow it back from the target and we kind of build backwards our solution. But now you might notice some issues with this algorithm. What you might notice is like when we did this breadth first search, like suppose our target location is here. We want to go here. Well, we see that we're searching an awful lot behind us. Like, why are we searching this area? This entire left area here, right? There's really no need to check this area here. If it was blocked, it would have been great because we don't need to check it because it's really going the wrong direction. And now this is where something like greedy algorithms come into play. We can show a comparison of why one is better over the other. So I'll show an example. Here we go. So let's say we have a simple map like this one, right? Greedy best first search gets to our target right away. But you see that this best breadth first search is still searching. It hasn't even reached the target. It doesn't even know where to go. So now we see that BFS is slow, but what we do know is that it's accurate, right? It always reaches the target eventually. It's just that it takes a matter of time, it takes a long time. But we see that with a greedy algorithm, we go straight for the target, and as Thomas mentioned, right? The greedy best first search kind of just goes directly towards it. It always goes straight, which is true here. But now we have some issues. What if we have a more complex map, right? If we play out this animation, we'll see that greedy best first search eventually gets to the target. Right? But the problem is that it doesn't give you the optimal path. You see that it goes towards the target and then goes backwards. And is wasting a lot of moves. And that's really inefficient. Especially like if you're playing hide and seek, right? You want to seek out the hiders. You really don't want to go in the wrong place and then backtrack to the places you've seen already and then go again. So this is why breadth first search might win in some maps. So now the question is, can we do a mix of both of these? Can we get fast efficiency like greedy searches, want it fast, but can we also guarantee that we have an optimal path? Guarantee that we always get to the place that we want to get to. So now this is where an algorithm known as A* comes into play. If you guys have taken CSE 100, you probably will have heard of A*. If not, you might have vaguely heard of it. It is a very common graph search algorithm, and I'll briefly talk about some of it. So the main thing you need to learn is understand the idea of a heap and a priority queue. So let me explain that real quick. Wait, just bear with me. I'm trying to change screens. Change, please. There we go. Alright. Ignore this algorithm on the right. It's just a brief. You can come back and look at the slides later. Alright, priority queue. So the key difference between an A-star algorithm and BFS is that an A-star algorithm uses a priority queue, whereas a BFS uses a queue. Now, to first understand a priority queue, we need to understand what a heap data structure is. So a heap is essentially a binary tree that is complete. What it means by complete is that at each level, so you see at each of these levels, right? We have this level where it says 100, which is a level where it says 40 and 50, a level that says 10, 15, 50, 40. Each level must be filled completely except for the last level. And another important part of the heap data structure is that it maintains either a min heap property or a max heap property. A min heap property is when every node is two children are larger than the node. And then for a max heap, every node's two children must be smaller than the original node. So we see on the left that we have a min heap. The 10 is larger than 15 and 30, the 15 is larger than 40 and 50. We see in a max heap, the 100 is larger than 40 and 50, the 40 is larger than 10 and 50, and so on. I don't think Gary taught priority queues or heap structures. Yeah. Depends on who you take the class from. But the idea, the only main thing you really need to know is that using a heap data structure, in constant time, we can get the smallest element or the largest element, depending if we use a min heap or max heap. And then, in order for us to add elements or remove elements from a heap, what we do is I won't explain the algorithm, but it takes log n time, or log n. Don't worry about how we solve that. Just know that it does take that time. Now, back to priority queue. So the reason why a priority queue uses a heap data structure is because a priority queue's main property is that when you pop from a priority queue, or you get the first element from a priority queue that you inserted, you get the element with the highest or the least priority, depending if you use a min heap or max heap. If you use a max heap, popping from a priority queue will give you the max element. If you use a min heap, popping from a priority queue uses a minimal smallest element. Now, for our purposes for A-star searches, priority queue will be implemented using a min heap, and we take the lowest priority element. And the way it works is like we store elements, or let's say for our priority queue, in our queue, we were previously storing nodes or like map tiles in a BFS. Instead of an A-star search, we'll be storing nodes in addition to a priority to it. So this algorithm on the right is really complicated. I'll walk you guys through it later in a minute. The idea is A-star is a combo of the greedy algorithm and Dijkstra's. Just think of Dijkstra's a little bit like BFS, but not really. It's also kind of a combo of the breadth first search. And because of time constraints, I won't go over Dijkstra's, but just know that Dijkstra's algorithm is a lot worse than A-star. A-star is just much better. So again, to reiterate, the key component is a priority queue data structure and a heuristic. The heuristic is just a measure that allows us to determine which direction we go to is most promising. So I'm gonna go back to the other page to show you like an animation of sorts. Give me a second. And I'll kind of introduce a bit more motivation as to why we use a priority queue. So I'll give you an example why we use a priority queue. So we see in this breadth first search, right? We're searching an awful lot of the map that we don't really need to search through. Like, I'll give you an example. Our optimal path ends up being this path here, right? But we ended up searching this entire internal side of this square, right? Like if you look at this algorithm, right? We're going through here, but we're even following this small crevice that goes backwards, and there's really no point. So the idea of using A-star is that we want to prioritize. We want to prioritize going the directions that are most promising. And we see that with greedy best first search, it actually prioritizes pretty well. it actually goes in a pretty good direction, but then it kind of veers off later. And we see that it's successful here. It always prioritizes the good nodes, and it stops once it reaches the target node. So now the question is, how do we implement this idea of prioritization? And how do we prioritize? Like, what measures are we using to prioritize? Well, we've seen that greedy search worked okay when we prioritize based on distance, right? Greedy algorithms are kind of prioritizing based on distance to the goal. Well, to ensure that we have the optimal path, right? The issue with the greedy pathing is that it wasn't optimal. The paths we found weren't optimal at all. Like if we look at here, it's not optimal. It's going through the wrong direction. So what do? We do an A-star algorithm, and we apply a priority. So with greedy best first searches, our priority is kind of just the heuristic, goal, comma next. Heuristic can be distance. It can be either the Manhattan distance, Euclidean distance, or whatever other distance measure you choose to use. Now the important part of an A-star algorithm is that we also store something called a cost so far. So like this map here. And what cost so far does is it stores a mapping from a node to the amount of cost it takes to go from the starting position to that node. So if you think about it, at the end of running through this whole algorithm, cost so far maps the target node to the least cost. And our objective with pathing is not only to find something fast, but also find it efficiently and also the most optimal path. And by storing these weights, right, the weights to go from one node to the next node to the next node, using this cost so far map, we are able to optimize our paths and choose the path that is most optimal. It's going to sound a little confusing, but I'll try to take you guys step by step. So let's look at this map here. I'm going to change this a little bit just to make it a little bit harder for the path. Let's make it like this. All right. So pretend this map is BFS. We see that the problem with BFS is that searching all of these tiles at the bottom and to the right here. That's kind of wasting our time. But now we see that this A-star search, right? All of these number tiles are tiles that we have searched, and it's searching a lot less than Dijkstra's. Unfortunately, it's searching a little bit more than greedy, but at least it's getting an optimal path. Whereas greedy best first search probably wouldn't get the optimal path. So now what do we do? To understand how this visual works, when you put your mouse on these tiles, the purple line is the cost so far. The other line, the line going towards the X target, is the heuristic. It is the cost to go, our estimated cost to go from our current node to the target. And what we do is that each of these tiles is numbered with the cost so far plus the distance to the goal. And so what we see is that what we do is we always search for the lowest path. So we're following from this 22, we go to 24, we see these 24s, but we don't look here. Do you know why? Because if we go here, the cost to get here is too high and is not rewarding because the estimated cost to get to the target is also really high. So we might as well go somewhere that we can reach fast and is also close to the target. And by being able to choose and prioritize the places that we can reach faster, we guarantee we guarantee that our path is optimal. And by choosing the path, prioritize the paths and directions that are closer to our target, we act a little bit greedily and end up just going towards the target much faster. So we don't have to we don't have to go around searching all these bad positions. So I can walk through the algorithm real quick. This is kind of like Python pseudocode. So first off, we have our came from map, remember from BFS. We use this to store a path. What it does is it just stores the path of least cost to get to that node from the previous node. And then we have our frontier. Instead of using a queue, we use a priority queue. And we start off by putting the starting node and give it a cost of 0 to make sure that we look at the starting node first. And so we do the same thing with the BFS, right? We check if the frontier is not empty. And while it's not empty, we get our current node. And a typical thing we do is that once we reach our goal, we just stop searching. So we do a break. So now here's the meat of the algorithm. In 7 lines, we do an A-star search. It's amazing. So what we do again, like BFS, is we first look at all our neighbors. So all of our neighbors of our current node we're at, and we call it next. So for each neighbor node next, we calculate the new cost. The cost to go from the current node to the next node. Now remember that this is like a recursive algorithm, almost kind of. We have a cost so far map that maps the cost to go to a certain node from the starting position. So really, if you think about it recursively, the cost to get to the next node is the cost so far to get to the current node plus the cost to move from the current node to next, which is marked by graph.cost, parentheses current comma next. And typically, like this cost is uniform. So, like for example, the AI competition running, the cost to go in any one direction is 1. But you'll see in later examples that I'll show later is that in maps with uneven terrain, where like let's say go from one position to the next position, costs more than another one. Like say like you have to go up a hill to go 1 unit to the right, whereas going up north is flat terrain. So obviously there's cost differences. And you want to get there faster. So A star also includes that, but I'll bring that up later. So now that we have our new cost, we have the cost so far we have the new cost to get to the next position. We now check if we have visited the new cost or we have visited the next node. So we know that cost so far stores a mapping from nodes that we have measured the cost so far to the cost it takes. So what we know from this is that every node key that's stored in cost so far is a node that we've been to already. So we just check if the next node is not in cost so far map. And if it is not in there, we proceed with the algorithm. And we proceed with the update step. So in this update step here, what we do is we update the cost so far because there is no cost so far already stored for this next node. So we store a new cost. And then what we do is we calculate priority. Remember, our priority is based on how long it took to get to that position plus the distance to our goal, or heuristic. So we do new cost plus heuristic, and then passing the goal position we want to go to and our next position. And then in our frontier, our priority queue, we put in our next node and attach it to priority. That way, our frontier will have our list of nodes that we want to check out in the order of priority. And then we update came from. We update came from to say that this next node we've been trying to go to came from this current node. Now, I also need to mention that there's another part that allows us to make the A-star algorithm optimal, which is storing, which is also checking if this new cost is less than the cost so far. So what you'll notice is that in addition to checking if the next node wasn't checked so far, if the next node was seen so far, like it was already seen, we already visited, we already added a cost so far mapping from it, mapping next to a certain cost. But let's say with our A-star search, we found a better path to that next node already. So sometimes in an A-star search, we'll actually revisit nodes. But the only reason why we ever need to revisit a node is if we found a more optimal path to that node. So that's why we stored a new cost, and if the new cost is cheaper than the one we have stored so far, we proceed with the same update step. We update the new cost. We update cost so far map with the new cost, just to tell ourselves that this cost is the actual true cost to get to this position. And then we update came from to tell ourselves that to achieve this lower new cost, we have to come from this current node. And we do the same thing. And then iteratively, if we apply that, we are able to get our most optimal path as fast as possible. Do you guys have any questions? I know A-star algorithm is actually a bit dense. Yeah, do you have any questions about A-star? All right. I'm going to talk a bit about the different, so for some maps, it's not always uniform cost. A BFS assumes uniform cost here, but as you see at this frontier line, it's even. It doesn't. So these green tiles are slower, they're like forests. You can think of them as forests that slow you down. But obviously, you don't want to go through an entire forest if you can just travel through around the forest and get there much faster. So you see that using Dijkstra algorithm, which is basically A-star, but a little slower, it finds the most optimal path by traversing around the forest. So the idea is that we've already visited, let's say like this node, this target node here, right? If we traverse through the forest, we would store a really high cost for the path, like let's say this path here, If we move through this path here, we would have stored a really high cost. And that high cost, while we've reached our target, it's not worth it. So that's why, like, with a A-star algorithm, we're also searching around the map. And because we search around the forest, we get to our target slower. But the good thing is, we update our cost so far, right? Remember how we did new cost less than cost so far? We do new cost less than cost so far because sometimes a path we find that goes to the same place we've already checked is a more optimal path. For example, here, a path going through the forest is not as optimal as one going around the forest, where it's much faster to travel. So in that case, by using new cost less than cost so far, we're able to get the most optimal path. Any questions about that? Okay, cool. Yeah. I'm gonna go back to my slides in a second. Give me a second. So I'm just going to conclude a bit on the pros and cons of each of the algorithms we went through. So the greedy pathing algorithm is fast and efficient. It's very cheap to measure. It's very cheap to find the next position to go to that's greedy based on greed. However, the main con is inaccurate because it doesn't even reach the target sometimes. And bug pathing, our next algorithm we introduced, is fast and efficient as well, not very hard to calculate. But the problem is that sometimes it introduces suboptimal paths, as I shown earlier. If you look at this slide here, if you look at this path here, it's a little bit suboptimal, right? We're kind of going all around the wall, but then in reality, we could have just gone around part of the wall, gone to the edge, and gone straight for a target. So that's an issue of suboptimality. And another issue with bug pathing is sometimes we go into loops. We never reach our final place. The next algorithm we introduced is BFS, which is like the exact opposite. It's a trade-off. It's a trade-off between your computational complexity, your speed, how much memory you're storing, and the optimality of the path you find and how fast you find it. So while BFS always finds the optimal path, purely because it searches every tile, right? It searches every tile of the map. It's very slow because it searches a lot of bad tiles. It searches a lot of directions that are not promising, and it has to store a lot of data. It has to store directions to every path and store the path. BFS stores every path from a starting node to a goal. So now we introduce the more optimal version, which is called A-star, which basically finds the most optimal path as well, and its speed is faster than BFS, but it's a little bit slower than greedy and bug. So it's like a balance between those two. And in fact, A-star is a very common algorithm purely because its balance is actually really worth it, and it achieves optimality. However, just a quick note is that A-star is very computationally expensive. So while it is faster than BFS, each step of the way for A-star is actually really slow. So like, for example, each step in evaluating BFS is really fast. It's just that we have to do a lot of steps. Whereas A-star does a lot less steps, but each step is very computationally expensive. And what I mean by step is like each step within that while loop. So like if I show you this algorithm, like BFS, right? Each step is like one iteration of the while loop. Same here, one iteration of the while loop in A-star where we check if the priority queue is not empty or not. Do you guys have any questions about implementation, pros and cons, anything? Okay, I'll get to the other algorithms in a bit. I won't be going through, so there's a lot of other pathing algorithms. Because of time, we only have like 10 minutes. I won't be going through them in depth. But I can kind of show you some demonstrations on some really cool ones. There's one called L1 pathing that's really cool. Yeah, actually, I'll just go through the other algorithm now. So these are just a couple of random other methods. Someone else from ASM.ai, Catherine, suggested Q-learning pathing, which is basically a reinforcement learning approach to learning optimal pathing from any location to a target location. So the main difference between Q-learning pathing and most of the pathing algorithms I showed today is that the pathing algorithms I showed today tell you the optimal path from a starting location to a target location, whereas Q-learning reads the whole map and tells you the optimal path from any location to your target location. So that's a little bit different. In particular, BFS also does the same thing. It actually tells you the optimal pathing from any location to target location as well. It's just very slow. There's another algorithm called jet point search. It's actually kind of complicated. I myself haven't read much into it, but think of it as a variant of A star that's a little bit faster. And then finally, the best algorithm I've ever seen of all of these that's actually faster than all of them is L1 pathfinding. So L1 pathfinding kind of sits in between these two algorithms. L1 pathfinding doesn't always give you an optimal path, but it always finds you a path. It's just not optimal. It's like 90% optimal. But the speed is much faster because the reason why is what L1 pathfinding trades off is that it spends a lot of time initializing to pre-compute special points on a graph/map to reduce the complexity of the map to less vertices and edges. And then all it does to find one path from one location to another is apply A star to a smaller graph, which makes it run much faster because if you have a smaller graph, running any search algorithm, graph search algorithm like DFS, BFS, or A star is going to be much faster. In fact, I'm going to show this algorithm because it's actually really cool. Let's see, L1 Pathfinder. Where's that link? Okay, bear with me. I need to open the website. Hello, do you guys hear me now? Hey, okay. I'm gonna go back to L1 pathing because I don't think I explained. Okay, so L1 pathing is a special algorithm that essentially pre-computes your map. It reduces the dimensionality of the map because remember, a map is really a lot of tiles connected by edges to other tiles adjacent to it. So what we see here is like these purple lines are connecting different little dots to reduce our map into a smaller graph that represent all the data we need to go from one position to another. So let's say we want to go from this green dot to here. It automatically computes the path really fast. And the way it does it is we draw a purple. So we first store all these special points called yellow circle, landmark points, corner points, and standard points. I won't go into depth of how those calculated because it's kind of complicated. There's a lot of research shown into this. The idea is that each of these points represent a key point and a important point. And the idea is that we have a line, edge, connecting 2 points, such as this point here and this point here, if and only if we can greedily path from one node to the next node. That's easily. So I'll give you an example. If you want to go from this green dot here to the red dot here, yeah, they're kind of like sentinels. They kind of like guide us in where we go. If you want to go from this dot to here, what we do is we run a A* graph search algorithm on the reduced map. So instead of running A* on the whole map, including every single map tile, every single square, we run it on these special points. Our special points forming the subgraph, forming the subgraph. And we kind of explore a subgraph instead. And with that in mind, we can efficiently explore the smaller subgraph much faster because it's smaller than the whole map, and we'll find the most optimal path. And the way, once we find this subgraph, right, we find this path in the subgraph, all we have to do now is go from each node in our path, that's represented by this white line, and run the greedy algorithm. Because by definition, each of these purple lines are connected, if and only if there's like a direct path to that direction. So once we apply A* to find their path in this smaller subgraph, we just apply greedy pathing each time. And it makes it really useful. And also, really interesting note, this pathing algorithm is actually fast. It was written in JavaScript, and it's faster than all the CPP algorithms. Like all the C++ algorithms are actually slower than this, which is really interesting. The jump point search algorithm, which is implemented in C++, is actually slower than this. But obviously, there's trade-offs. The main trade-off of the L1 Pathfinder is that it's a lot more storage, and the initialization time for it is very long. You have to pre-compute the whole map first. So anyway, that's all I'm gonna share about AI pathing today. Do you guys have any other questions? All right. How do you become godly? Asking the wrong person. Yes, you cut bread. That's all you do. I went in there. Alright. We're gonna cut some bread. No, I can't get 50%. It's too hard. Literally impossible. Yeah, but this workshop's also really helpful for the hide and seek competition we're running. Let's say like if you want to go from one place on the map and you want to search another place, to actually get to that place, you need to apply one of these algorithms and run it, right? That's just a quick note. Yeah. Do you guys have any other questions? I'm gonna stop cutting bread. Yeah, I need to pause recording, so guys. Thank you for reminding me.